The focus of this unit is on looking at free radical halogenation of alkanes. By the end of this, you should be able to predict the products of radical halogenation reactions of alkanes, and you should also be able to report the mechanism, that is all of the steps that are required to go from the starting material of an alkane to the final product, which will have a halogen atom incorporated. So let's get started. First off, just a reminder that when we're talking about free radicals, what we're referring to are molecules that have an unpaired electron. And as we walk through how these reactions take place, what we're going to see is that the intermediates will each have one or more free radical species generated as a result of the reaction steps that are taking place. So first off, let's take a look at the net reaction that's going to go on here between alkane and a halogen. Specifically, the halogens that we generally focus on here are chlorine, that is Cl2, and bromine, Br2. So our general reaction that we're going to look at and use as a way of exploring radical reactions is going to be that we'll take an alkane, such as, we can abbreviate here by showing a CH bond, and then that carbon to be an alkane has to have a total of 4 groups bonded to it, and we're going to plug those in as R groups. So the R groups here can be either alkyl groups, which could be something as simple as a methyl group CH3, or they could be hydrogen atoms. It doesn't matter which. So in other words, we have to have an alkane here, and the alkane absolutely has to have at least one carbon-hydrogen bond going on. So that's why I've put that in there specifically. There has to be a carbon-hydrogen bond. And what's going to happen during this reaction is that the carbon-hydrogen bond is going to get replaced with a carbon-halogen bond. So we're going to put in the reaction arrow here and fill in our reactant as Cl2 or Br2. And I'm just going to abbreviate this for purposes of writing out the reaction product as X2. X is commonly used as an abbreviation for a halogen. And this reaction also requires light and heat, which we're going to abbreviate just like so. So our light and heat gets abbreviated like that. The light and heat are important because they are going to enable the formation of radicals during the course of the reaction. They're going to require the energy to get that process going. At the conclusion of the reaction, we're generally going to be most interested in the main organic product. And that organic product is going to correspond to the replacement of a hydrogen atom with a halogen. So I'm going to fill in X here. And what we're keeping in mind is that we replaced the CH bond in the initial molecule with a CX bond in the final product. And that X can be the chlorine or the bromine atom. So we're going to take a look at an example problem or two of this using some actual atoms filled in here. And we're going to start by looking just at ethane, CH3, a 2-carbon alkane. We're going to react that with Cl2 in the presence of light and heat. And we could ask as a question, what is going to be the major monohalogenation product of this? So monohalogenation, of course, means bring in one halogen atom. So we're asking for the monohalogenation product. The reason that I specify monohalogenation product here is that if we let the reaction go long enough and have an excess of chlorine available, we could technically replace many of these carbon-hydrogen bonds in the alkane with carbon-chlorine bonds. So mono, of course, means that we're just looking for a halogenation product that has one halogen incorporated. So in order to predict that, what we're going to do is replace one of the carbon-hydrogen bonds with a carbon-halogen bond. So CH3 becomes CH3 CH2, because we've gotten rid of one of those hydrogen atoms, Cl. And if we look back up at our general reaction and you're interested in balancing the equation, we could also put here as a product HCl. Just like in our equation up top, we could have put HX to balance out that equation. Generally, we're going to be most interested in what organic product forms as a result of these reactions, so that's why I focus primarily on looking at what's happening to the carbon atoms along the way. So we've gone from ethane to 1-chloroethane, this molecule here at the right-hand side of the page. So in that case, you can pick any of the 6 hydrogen atoms in that molecule of ethane and replace it with a chlorine atom, and you're going to get the same exact product, the same constitutional isomer, regardless of which of those individual hydrogens you choose to remove and replace with a chlorine. But if we make the problem a little bit more complex and we instead choose to go after a molecule that is not so symmetrical, that has a bunch of different types of hydrogens present in a bunch of different places, we run into a situation where we have to ask ourselves what is going to be the preferred product of the reaction. So we're going to draw out here a molecule that's a little bit more involved, a little bit more complex, and I'm drawing this out as a condensed structural formula just to emphasize where all the hydrogen atoms are. You should also certainly be prepared to work with this starting from a line angle formula also. So we've drawn out the complete structure here for 3-methylhexane, and we're going to react this with our halogen. This time I'm going to use Br2. Fill in my light and heat symbol. And then we have to ask the question of which hydrogen atom are we going to replace in order to create the monohalogenation product? Because we have a variety of different hydrogens in the molecule, and replacing each of those with a halogen would give a different constitutional isomer, depending upon whether we choose to replace the hydrogen here, 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 here. You get the idea. So there's a bunch of different options here for which hydrogen we could replace with a halogen. And we need to know what is going to be the selectivity of this reaction, which hydrogen is going to be the preferential one to remove and replace with a bromine. And the one that we're going to replace with a bromine is going to be the most substituted carbon atom. So what you'll do is look here for the most substituted carbon is going to be the position that reacts fastest in a halogenation reaction. So looking at the different carbons here, remember that we have the primary carbon that's bonded to just one other carbon, secondary carbon, and tertiary carbon. Tertiary carbons are going to react the fastest, so we're going to look for a tertiary carbon that's directly bonded to a hydrogen, and we have just one in the molecule that's going to be right here. That's our tertiary carbon. The others in this molecule are all primary or secondary carbons. So it's going to be this location that we've highlighted in green, that tertiary carbon, that's going to react the fastest. So when we're looking at the reaction rate here, the rate of the reaction is going to be fastest at a tertiary carbon. So it's fastest at a tertiary carbon, second fastest at a secondary carbon, and slowest at a primary carbon. So in predicting the monohalogenation product based on the reaction rates that can occur at each of these carbon atoms, we can predict that the major product of this is going to correspond to replacing that carbon-hydrogen bond at the tertiary carbon with a carbon-halogen bond. So let's go ahead and do that to write out our final product here. And a key thing as you are learning about reactions, there's going to be a lot of reactions that we talk about in organic chemistry, and it's important to keep track of all of these and keep them sorted out. And one way to do that is to focus on what functional groups are present and what reagents are coming in. So here, the general paradigm that you would see would be what's at the very top there, that you have an alkane to start with, reacting with a halogen in light and heat, and that's always going to give you a halogenation reaction, free radical halogenation. So we've gone ahead and I've drawn out our material here, and now I'm going to replace that hydrogen that was present in the starting material with our halogen. So we replaced the hydrogen with a halogen. If we were writing out the inorganic product of this reaction, it would be HBr. Generally, we're just interested in writing out the organic product of the reaction is what we typically focus on. So if you were asked to provide the major organic product of this reaction, it would be what we're circling here in red. This is our monohalogenation product that we would expect to be the major product of this reaction. So we can ask the question of why is it going to be the case that the reaction takes place fastest at a tertiary carbon? And in order to answer that question of why the reaction takes place the fastest at a tertiary carbon and slower at secondary or primary carbons, what we need to do is look at the mechanism of the reaction. The mechanism is a step-by-step map that illustrates how the reaction is taking place. In other words, what are all of the intermediates that form along the way and going from the starting materials to the very final product? What's the step-by-step pathway that the reaction undergoes? And this mechanism has to explain any observations that we can make about the reaction, such as the observation of the selectivity of this reaction for taking place at a tertiary carbon over a primary or secondary carbon. And by the way, a term that we should throw out here when we're referring to the fact that we have a preference for one constitutional isomer over other possibilities is the term regioselective. We would describe this reaction as being regioselective. So selective means that the reaction is choosing a particular outcome over others, and regio is referring to the possibility of making different constitutional isomers by putting the bromine in different spots or the chlorine in different spots. So regioselective indicates that the reaction hypothetically could yield multiple constitutional isomer products, but in actuality, one of those is preferred over others. So reaction could hypothetically yields multiple constitutional isomers. In other words, putting the bromine in different spots along that chain. But in actuality, prefers one. And we could actually broaden this out and say, but in actuality, prefers one or some of those products, not all of them. So in other words, we're not just randomly replacing a carbon-hydrogen bond with a carbon-bromine bond. We've selected which carbon atom is getting that bromine atom. So we would describe the reaction as being regioselective. And we're trying to answer the question of why that reaction is regioselective by writing out a mechanism for this reaction. So we're going to use this example to write out the mechanism for how this reaction takes place and why it is the case that we selectively replace that tertiary carbon-hydrogen bond with our bromine. So we're going to write out the mechanism. Mechanisms are something that we will learn for a variety of different reactions. They're a useful tool for predicting what products you would expect to generate from a reaction. And when you're thinking about mechanisms, it's best to try to focus on understanding why each step is happening rather than trying to memorize each step, because we're going to learn so many mechanisms this semester that if you don't have some cues and clues to think about and frame what the mechanism is going to entail, you're going to have a really hard, impossible time trying to just memorize step by step by step, because we're going to be doing so many of these. So try to understand as we go through what's going on at each step. This mechanism, by definition, is going to be our step-by-step pathway to go from the reactant to the product. So it's a step-by-step reaction pathway. So in step 1 of the reaction mechanism, what happens is that when we place Br2 or Cl2 in the presence of light and heat, the weak bond connecting the two atoms, the two halogen atoms, is going to break. And so we can show that in step 1, which we will describe as an initiation step. I'm not going to explain right now why this is called an initiation step. We'll go back and return to that later after we get through the mechanism. But for now, we'll just go ahead and label it as initiation. And initiation is going to be the step where the bond between the two bromine atoms, or if we were using chlorine, it would be the two chlorine atoms, breaks in the presence of light and heat. Light and heat provide the energy for that breakage to occur. So we're going to go ahead here and show that this covalent bond between the two bromines is breaking. One of the two electrons from that covalent bond comes over onto the bromine on the right. The other one comes to the bromine on the left. And I'm showing this with a single-headed arrow to indicate the movement of one electron. We have 2 electrons total in the covalent bond, and we're moving 1 electron to each of the 2 bromine atoms, and so therefore that's why we have the 2 single-headed arrows going on. So the product of this reaction is going to be 2 bromine radicals. So we'll go ahead and plug this in, 2 bromine radicals, and I'm going to emphasize that we are creating radicals by putting that unpaired electron in red. And this species is going to be quite unstable. This is the same type of species, by the way, that if we're thinking about the destruction of the ozone layer by halogens, what happens is those halogens within the ozone layer, they're subject to a lot of light and heat. They form radicals, and those radicals are highly reactive and going to react with the ozone layer. So in the case of what we're doing here, for purposes of organic chemistry, we're focusing on the reaction of these radicals with carbon atoms, specifically carbon-hydrogen bonds, but this is also a general concept that's important environmentally as well. So at step 2 of the mechanism, we're going to describe this step as being a propagation step, And again, I will go back and define what we mean when we say a propagation step a little bit later on. We're just filling this in so far for purposes of our notes. So our bromine radical is supercharged, extremely eager to react. And so what it's going to react with is whatever bond within the alkane it can react with that's the weakest and going to lead to the most stable intermediate. So let's go ahead and draw out again our alkane molecule. And our observation was that in the final product we would replace the carbon-hydrogen bond of a tertiary carbon with a carbon-bromine bond. I'm going to draw that carbon-hydrogen bond of that tertiary carbon out explicitly there to the bottom because that's what we're going to be targeting here at this step. And so we're going to go ahead here with this. Our bromine radical is really eager to react, and what it's going to do is grab one of the hydrogen atoms from this molecule to create a carbon radical intermediate. So the bromine radical here is looking around for a hydrogen to form a bond to. It's going to form a bond to this hydrogen here at the tertiary carbon. So we show the bromine coming over, it's donating one electron to formation of this bond, and so we show a single arrowhead there to indicate the donation of one electron. The other electron to make the covalent bond between H and Br is going to be donated by the hydrogen here, so we use a single-headed arrow, showing that the hydrogen and the bromine are teaming up. See how those arrows are coming together there at the middle? That's illustrating that we're forming a bond using one electron from the carbon-hydrogen bond and one electron from the bromine radical. So we do that, and then we have one electron left here in this covalent bond, and when we have one electron left, it has to go somewhere, and the somewhere that it's going to go is onto the carbon atom right there that it's bonded to. So we'll show that electron from the covalent bond coming up and landing on the carbon. And when we're showing these arrows, we want to make them as accurate as possible. So I'm showing that single arrowhead in blue with the arrowhead pointed straight at, smack dab, that carbon atom that radical electron is going to land on. The purpose of these mechanisms and the electron pushing arrows is to be able to build a map for what's going on, and so we need to make sure the map is unambiguous. So I'm drawing out what would result from this particular step. So drawing out the intermediate that results from the mechanism step that we just showed the arrows for, and I'm going to go ahead and put my radical electron on the carbon right here in blue. That's color-coded the same as the electron pushing arrow was in our mechanism. Additionally, as a result of this step, we've also created HBr, where our bond connecting the H and the Br was formed using the red arrows that we've shown at left there. So at this point, we could ask ourselves and address the question of why it is the case that the reaction occurs fastest at the tertiary carbon and slower at a secondary or primary carbon. In other words, why are we showing at this step that the reaction is occurring preferentially at this carbon-hydrogen bond at the tertiary carbon that I've highlighted in green there in the bottom structure? The reason is that of the different possible intermediates that we could form here, the carbon radical intermediates, the tertiary carbon radical intermediate is the most stable possible. It's more stable than a primary or secondary carbon radical. And so that's going to be the one that forms preferably. So it's going to be more stable. A tertiary carbon radical, which I'm putting a dot there to indicate tertiary, is more stable than a secondary and more stable than a primary. And so it's the most stable and it's going to form the fastest. It has the lowest energy barrier that it has to get over to get to that carbon radical. And so it's going to form really quickly. And it's forming more quickly than the other possible carbon-hydrogen bonds that we could break in this molecule. And so this is the step where we introduce the regioselectivity. This is where the reaction preference for replacing a tertiary carbon-hydrogen bond with a bromine takes place. So we've created our most stable carbon radical at this point. So that's going to be the point of step 2, is going to be to create the most stable possible carbon radical as a result of this. And that most stable possible carbon radical is going to be the one that corresponds to placing it at the tertiary carbon. So we're creating the most stable carbon radical. And even though that is the most stable radical that we can make here, a radical is certainly not going to be a super stable molecule that's going to persist for a long period of time. Instead, it's going to itself be very eager to react. And so what's going to happen is that carbon radical would really like to react with something else to continue onward. And so that's going to lead us to step 3 of the reaction mechanism, which we also call a propagation step. And again, I'm going to go back in at the end and define why we refer to this as a propagation step. So we're going to go ahead and copy out what we are using from our previous step, that is the carbon radical molecule, into this step of our mechanism. So we're going to fill all this in. And fill in my radical. So this radical is looking for what is available in the reaction mixture that's most abundant for it to react with. And if we start thinking about what's present in a reaction container at the initial stage of the reaction, it's going to be millions and millions of molecules of chlorine or bromine and millions of molecules of alkane. And so what this carbon radical is most statistically likely to come into contact with at the onset of this reaction is going to be either another alkane molecule or a Br2 molecule. If it comes into contact with another alkane, it is not going to react super fast and super favorably, but if it comes into contact with a Br2, remember that bond connecting the 2 bromine atoms is a relatively weak bond. In other words, it's relatively easily broken, and specifically it's easily broken homolytically like we did in the initiation step. And so what happens here is that the carbon radical is going to react with Br2. And you may be having a little bit of a freak out right now because you may be saying to yourself, wait a minute, in the net equation for the reaction, we took 1 Br2 plus 1 alkane to give us, in the net reaction at the top left corner, 1 haloalkane plus HBr. And in the mechanism, it looks like we've used 2 Br2 molecules so far because we used it at the initiation step and we used it at the propagation step. What you have to keep in mind here is that we're thinking container-wide. We're thinking what's statistically most likely to happen here in this container that has millions and millions of each molecule. And so statistically, at the onset of the reaction, when there's plenty of alkane and plenty of Br2 available and relatively small amounts of these radical intermediates present, what's going to be most favorable to happen is that the radical carbon is going to react with Br2 at this step 3 called propagation. So that's what we're going to show happening here in this so-called propagation step. So what we will do is we'll take our unpaired electron from the carbon. It's highly reactive, very eager to form a bond to something. It's going to come over, and it just happens that this bromine-bromine bond is very weak and prone to breaking homolytically, so it's going to donate 1 electron to come over and team up with the carbon atom. So what we're showing here with the 2 red lines is that the carbon radical and 1 of the electrons from the bromine-bromine bond are coming together to create a carbon-bromine bond. The other thing that has to happen here is this other electron from the covalent bond goes somewhere. It has to go over to the bromine on the right. So we're going to go ahead and draw out the products that result from this step. So we'll draw out our bromine radical. And by the way, you could calculate the formal charge on this bromine radical. You're going to find that it is 0. And we're also going to go ahead and write out our organic product of this step. So that's going to correspond to plugging in that bromine there at carbon number 3 of the chain. So I'm going ahead and writing out the product that would result from this reaction. And I'm going to fill in my bromine atom in red here, we'll choose for emphasis. And we've plugged in that bromine, the covalent bond there, as a result of the electron pushing arrows that we show in red there at that step. So at this point, we've shown how to create our major organic product that we would observe from this reaction. And that's usually our objective with writing mechanisms, is to show how we form the major product. We've shown how we form the major product here. So this generally could be the end of the pathway of showing the mechanism, because we've justified how we go about going from our starting material of Br2 in a container to our final product here where we've brominated our alkane. So I do need to mention additionally that the reason we call these propagation steps and initiation steps is if we take a look at what we're calling step 3 here, one of the products of step 3 is bromine radical. So at step 3 here, in addition to forming our organic product of interest, we've also formed bromine radical, which I'm highlighting there in red. The relevance of this is the bromine radical is still highly reactive here at the end. And so what it's going to do is it's going to, if you look back at the reaction mechanism and see where bromine radical is involved as a reactant rather than a product, we see if we go back to step 2, that in step 2, we have bromine radical acting as a reactant right here. And so what happens is that bromine radical that results as a product of step 3 is able to re-enter the mechanism at step 2. So we're going to say this re-enters the mech at step 2 of that mechanism. So this bromine here pretty much can just come on over back to here to re-enter that reaction mechanism. So in other words, that bromine radical that we've generated as a result of step 3 can then go in and react with another molecule of alkane at step 2 to generate another radical carbon. That radical carbon then goes on to step 3 to result in the breakage of another bromine-bromine bond. That process creates another bromine radical in addition to the organic product, and that bromine radical can again enter back into the mechanism at step 2. And so what you end with here, and the reason we call these propagation steps, is because they can cycle through. So we can cycle through from the bromine radical back to step 2, on to step 3, and we can just go around and around in a circle here like I've drawn with my green arrows, where you go from propagation step 2 using that bromine to create a carbon radical. Then at step 3, we're generating more bromine radicals. So it just goes around and around and around. And so the reason we can call these propagation steps is they are self-propagating. After the initiation step is what it takes to get the reaction going initially, but once the reaction is up and underway and cooking, we don't need the initiation step to take place any longer. Steps 2 and steps 3 are self-propagating. So we refer to the initiation step as what's required to get the reaction going. We need a source of at least a little bit of bromine radical, but from there the reaction propagates onward and onward. And this is one of the reasons why the destruction of the ozone layer by radicals is particularly harmful and particularly prevalent, is because of these propagation type reactions that can take place. So it just requires a relatively small amount of radical formation and initiation to then get the steps 2 and 3 propagated and propagated over and over and over again. So these propagation steps will occur until we reach the end of the container, where we reach nearly the last little bit of alkane or the last little bit of bromine that is present. And when that happens, what we transition to is a phase of the reaction referred to as termination. So termination is what's going to happen when we start to reach the limiting reagent of the reaction. In other words, when we start to have used up every last bit of one of the two reactants, the alkane or the Br2. So that leads us to the so-called termination reaction. The termination reaction step is only statistically favorable when we have used up the majority of our alkane or the majority of our Br2. So the termination step is going to be the step where any two radicals join together. So it's going to be where any two radicals join together. And the relevance of this and why we call it termination is that once two radicals have joined together, the reaction is going to stop because there's going to be no more radicals to participate in the propagation process. So there are several examples of termination type steps, and which one of these is statistically most favorable is dependent upon what the limiting reagent is and how much of each of these species are present. So it's totally reasonable to write out any of these different possibilities as your termination steps. So termination step could include linkage of our carbon radical, which would be this right here as a line angle formula. This is the same as the carbon radical we were drawing earlier in step 2 as a product, except that we've drawn it as a line angle formula. So that's one intermediate that could be present. It could be looking around for a Br2 to react with. It doesn't find any Br2 to react with, and so instead, perhaps what it could come in contact with would be a bromine radical. And so if it comes in contact with a bromine radical, what's going to happen here is the bromine radical unpaired electron is going to come over and team up with the unpaired electron of the carbon. And this step is generally statistically favorable only in cases where we're nearly reaching the end of the materials that we have available in the container to react. Prior to that, it's going to be statistically more favorable for the reaction of the alkane radical with a Br2, because the Br2 is going to be more abundant than the bromine radical. So when we're reaching the end of the line here, we can get a termination step joining the carbon radical with a bromine radical. We could also, if we had at the bottom of the container just bromine radicals left as the most statistically likely things to come into physical contact with one another. And if that were the case, we could take a bromine radical electron from here and here, join those together using that single-headed arrow, and show the formation of Br2. And as a third possibility here, what could happen is that we could join together two carbon radicals. So we're going to take our carbon radical number 1, which I'm going to show a red unpaired electron here. Carbon radical number 2, which I'm going to show in blue here for emphasis and so that we can map out who's going where in the reaction. I'm going to put its unpaired electron as a red dot there. And this would happen if we had no or very little bromine left over, so that statistically it was most favorable for these two radicals to come into contact with one another. So the unpaired electron from that carbon comes over, teams up with the unpaired electron from the other carbon, and that's going to create a covalent bond between those two carbon atoms. So we've created a new carbon-carbon bond there. And I'm going to draw out the product of this reaction, trying to color code it according to what we did in the earlier, in the left with the blue and the black. So I've drawn out the skeleton of my black structure, and then what I'm going to do in red is show the covalent bond that we've just formed. So that's the bond that results from joining those two single-headed arrows, the two unpaired electrons. And then we're going to draw out in blue the structure of the additional molecule that we've joined up with it. So that additional molecule had a methyl group, it had bonded to it an ethyl group, and it had bonded to it a 3-carbon chain. So we're going to go ahead and draw that out like so. So in other words, as we're looking at this and drawing this out, we had our carbon atom right here that was connected to a 2-carbon chain. That's the 2-carbon chain right here. Methyl group connected to it, that's right there. And then propyl group here, 1, 2, 3, 1, 2, 3. And that red bond that we're showing right here corresponded to the electron pushing arrows that we're showing in red there. So we're showing the connection between the two carbons. And then the part of the molecule that I've shown in black over here, our 6-carbon chain, corresponds to the 6-carbon chain over here, and corresponds to that methyl group right there. So we've drawn out this as a possible termination step. So again, which one of these termination steps is most favorable depends upon which of these species are most common in the reaction mixture once we have exhausted the majority of our alkane starting material and our Br2 starting material. That's when we're going to see this termination step take place. And